to talk about mirrors and lenses. I'll solve or I'll draw a ray diagram for each type of curved mirror and lens, and then I'll solve a problem um, for each type as well. So that's kind of how the lesson's going to be structured tonight. But before that, I wanted to kind of, as always, do some housekeeping and just kind of talk to you guys about how the rest of the semester is structured, because we're getting to that point. So I'm going to kind of go through the dates. So our next due date is November 1st. Okay, and on November 1st, you guys have your um, everyone has their simple harmonic and waves test. Okay, so that's a due date, and everyone, regardless of what section you're in, 12 week is rapidly catching up to the other sessions. We'll have your waves test due tomorrow. Okay, on November 8th, that's not this week, but next week, everybody, this is a due date, so it's a Wednesday. Everyone again will have their EM and optics test. Okay, let me make sure I'm getting this right. I looked at it earlier today, but I feel like okay. Yep, I'm right. Okay. So your EM radiation optics test, the stuff we're talking about tonight will be on this test. Okay, this EM optics test. On November 15th, that's also a Wednesday. This is your last due date before not spring break, Thanksgiving break. Okay, and everyone will have their electricity and magnetism test too. Okay, then from November 20th to the 24th, which is basically the week after, that is Thanksgiving. So we don't have any class. No due date. But this is a great time to start studying for the final exam, maybe work ahead a little bit, work on your test corrections, ELOs, that kind of stuff. If you've got some extra time, you might as well work on that kind of stuff. Okay, because when we get back from Thanksgiving is fast and furious. Okay, so the first due date after Thanksgiving is the 29th, and that's a Wednesday. There are no tests due, but you guys do have assignments. Now, this is where it gets kind of weird. December 1st, which is the Friday that week, you guys do have a due date. This is your very last due date, and your nuclear physics test is due. And that's for everyone. Okay, and if you miss that due date for whatever reason, usually you get 3 days to make up your work, right? But because this is the end of the semester and everything has to be in by before the final exam starts, December 5th is the very last day for any sort of late work, for test corrections, even if you have extended time for some reason due to some sort of accommodations, it does not matter. Regardless of who you are, December 5th is your very last day for late work. Test corrections, everything. Do not ask me on December 6th to take your test corrections or your ELOs from watching these sessions or anything like that, because I can't. It's virtual policy that I cannot take anything after December 5th at midnight on December 6th. So basically you have till 11:59 on December 5th. All the folders will close. The Dropbox folders will close. The test folders will close. Everything closes. You couldn't submit something even if you wanted to. Okay. Then the next day, December 6th and 7th, that's a Wednesday and a Thursday, is your final exam. Okay, so this is your window to take the final exam. You must take it within these 2 days. There's no 3-day late window for the final exam, nothing like that. You have to take it all in one shot. You can't close it and come back to it. And it's worth 20% of your grade. Okay, so it's worth the same as every single lab that we've done this semester. So it's a big chunk of your grade. And that's December 6th and 7th. Then that Friday that week, the course will close. You guys will lose access to the course at midnight, December 8th. Midnight December 8th. Well, like midnight December 9th, really. You get to 11:59 on December 8th. And then you guys lose access to the course. You can't get anything out of it. You can't put your feedback or anything like that. And then Saturday, I can start grading your final exams. I cannot grade your final exams until the course has closed. Okay, that's virtual school policy. So don't email me on Thursday and say, I took my final yesterday. Can I know what I made? No, I'm not allowed to grade it. Okay, I can't grade your finals until Saturday. Okay. That also means that you guys won't be able to see what you missed on your final exam. It's kind of like if you take an EOCT or a milestone test, you submit that test and you get your grade back later, and it doesn't tell you exactly what questions you missed. The final exam is kind of the same way. Okay. Now, let's talk about when we're going to review for the final exam. These are the dates that I will be reviewing for the final. Excuse me, November 14th. I'll be reviewing for the 1D motion test, the 2D motion test, and the Newton's Laws test. On November 28th, this is after Thanksgiving. It's a Tuesday. I'll be reviewing for application of Newton's Laws, energy, momentum, and the first half of waves. And then December 5th, this is the day before the course access or all the Dropbox folders and everything closes. I'll review for the waves, electromagnetic radiation, electricity, and nuclear tests. Now, for the final exam, because I want you guys to do the ELO for the final exam. Okay, there's a Dropbox folder that says like final exam review 1, final exam review 2, final exam review 3. You answer the question. Okay, so you solve, including work. A question from each of these, from each test that was covered during the final exam. And then from each test covered during the review. And I will add 1 point to each test. Which makes it about like 2.5%. About, not exactly. This is a great way to not only review for the final, but also boost your grade as high as it can go before you take that final exam. Okay? So that means you can get a point for the first one. If you answer the 3 questions, you'll get a point on your 1D motion test, a point on your 2D motion test, and a point on your Newton's Laws test. Okay? So that's a great way to review for the final and to boost your grade a little bit. Okay. And it doesn't seem like a lot, 1 point, 2.5% to each test. Remember, your test is 40% of your grade, right? So that's actually that's the best way that I can add points to your grade because, if I were to add points to a lab or something like that, it wouldn't be worth nearly as much as adding points to a test. Okay. But you have to do the ELO for it. You can't just attend the session. You can't just, you know, say that you watched it. You have to do the ELO. And this is so, I have some basically like written proof that you did the final exam review or you watched it or whatever um, for my bosses. Okay. So this is a great way to get some extra points for the final. Now, this one on December 5th, remember that's the day the course access closes. So I'll get the review up as quickly as possible, or you can attend the live session. And the questions are already will be already posted ahead of time, so then you could answer them as we go along, or you can answer it, that night or whatever. But so this one will have to be due the same day, okay? And that's just the way virtual school works, okay? So that's kind of the housekeeping stuff I wanted to chat with you guys about today. And now I'm going to get to the actually, let's learn some stuff. Okay. So let's see. So plane mirrors, this is another way to say just a flat mirror. Okay. My, like the kind that you have in your bathroom. Okay. So a lot of this for plane mirrors might be something that you already know, right? So the image type for a plane mirror is virtual, which means you see that image. Basically, it means you see the image in like Mirrorland. So your image isn't like standing right next to you. You see your image on the other side of the mirror. Okay. Your image height is the same. Okay. When you see a image in a flat mirror in your bathroom, it looks the same height as you. It looks identical to you, right? And the orientation is upright. Wouldn't that be weird if when you looked in the bathroom mirror, it showed you upside down? Wouldn't that be hard to like brush your hair or put on makeup or whatever? So that's a flat mirror. Okay, this is the kind you have in your bathroom. Okay, so let's go to the next one. Those were pretty easy. Now let's talk about curved mirrors. These are the formulas you will use for curved mirrors or for lenses. And there should be a negative right here. And so this is the formula here for, it's called the thin lens equation, but you can use it for curved mirrors. And then you have this one, which is technically called the magnification equation because you can go like this. Okay, and then this lists what all the variables are, but we'll talk about that more when we get to each of those sections. Okay, so just remember there should be a negative right here before this DI. Okay, now this table is really important. Every time that you're trying to work through a mirror problem, you're going to want to come back to this table and look at it. So for example, a concave mirror is going to have a positive focal length. So when you do the math, you need to make sure you show a positive focal length in order to get the right. That's how we can use the same two formulas for convex, concave mirrors and convex and concave lenses because we adjust the signs accordingly. Okay, and we'll see that a little more when we do the math. Now, let's go right here and let's try and draw a diagram. This is called a concave mirror. Concave mirrors basically form like a cave. is the way I think about it. You know, you could like hide in this cave or whatever. Um, so that's a concave mirror. Now, when you draw your ray diagrams, I highly recommend that you use a ruler. Unfortunately, in this software, I can't use a ruler, and so my lines are going to be a little squiggly, but you should use a ruler. Okay, so here we go. For a concave mirror, there are 3 lines that you can draw, and where they intersect is where your your image is at. Okay, so and mine might not work out exactly right because you know my lines are squiggly, but I'm gonna try my best. Okay, so I'm gonna do this. I'm gonna continue this one out like this. Okay, so that's the first set of lines. Okay, now I'm gonna draw another set. Okay, so this one, you see how this one we went parallel and then we went through that focal point. That's what this is called, a focal point. Okay. Now the second one, we're going to go through the focal point and then parallel. Okay. This one's not coming out right, I can tell. So I'm going to make it, uh-oh. Yeah, I had that one so well too. I was really proud of how flat-ish it was. Okay, so there we go. Now this one, I erase. Okay, so I'm going to try my best to go through this line. I already see it's not super straight, but it's the best I can do with this pen. Okay, and then I'm going to make a parallel as much as I can. Okay, so this should be straight. You know, you should use a ruler, and then you'll have a parallel. So you'll go parallel, angled through the focal point, and then you'll go angled through the focal point, and then parallel. So you kind of do 2 different lines. And you see they both start at the top of our object, which is what that arrow is. It's called our object. Okay, and now let's do one more. You really only need to do 2, but we'll do 3 just for the fun of it. And I can see right now that they might not match up. But basically, the third one is just a straight line through this center of curvature. Okay, so really, all 3 of these, you know, should meet in the same spot. This one didn't. Oh, oh dear. Let's try that again. Okay. And then we'll go. So note to self, don't try and erase anything. And then I'll go over here. And I'll do my pink one. Okay, so you want them to all end up in the same spot. These obviously didn't because you know they're not super straight, but you'd want them. So wherever they met, let's say these look the 2 straightest. So let's say they met right here. All 3 of them met right here. Then you would have your image right here. So your image would be an upside down arrow right here. Okay. So that's how you would draw it. So, and you really only need to draw 2 of the 3, but I'm showing you all 3 just to kind of help you out. And you can draw your 2 favorite. Now let's see. This is kind of a summary of what they should look like. So I just did one example. Okay, so this was farther than C. Okay, farther than F and C. You could have an object between F and C. You could have an object at F. You could have an object closer than F. And each one will kind of depend what's going on. The only thing is at F, you will have no image. Okay, because all those lines, right, needed to go through F. So if your object is on F, it can't go, you can't have a line going from your object to F, and so you'll have no image there. Okay. Now let's try and do a math problem using these using these values. Okay, so this is going to be our focal length. And then we have an object with a height of 2 centimeters. I'm going to call that my HO. And it's 25 centimeters from the mirror. So I'm going to call that my DO. And then I'm going to want DI, which is my image distance, and my image height. Okay. So my focal length is 20 centimeters. My height of my object is 2 centimeters. You see I'm leaving a little space because I'm going to go ahead and put my charges in there, or my plus or my minus. My object distance is 25 centimeters. And then I'm looking for DI and, looking for DI and HI. Okay, so if I go back to my chart, I see that for a concave mirror, my focal length is positive. So I'm going to put a plus there. I see that my object height is positive because it's upright. And then since my my object is 25 centimeters from the mirror, it's also going to be positive. Okay, so now I can start, I can do the first step in solving this problem. Okay, so I'm going to do that. I'll do it right here. Okay, so I'm going to use this formula. Okay, now I'm just going to plug in my numbers. And if you want to put DO in front of DI or whatever, you can, because it's positive, we're just adding them, it doesn't really matter. Okay, now I have this. I hate fractions. I don't know about you guys, but I hate fractions. So the first thing I'm going to do is I'm going to transform this into a decimal because it's easier for me to, add and subtract decimals from each other than fractions. So I'm going to do 1 divided by 20, and I'm going to get this. I'm going to do 1 over 25, and I'll get that number. Okay, now I'm going to put these two numbers together. Because, we want to put like things together. Okay, so I'm going to get 0.01 is 1 over DI. Now, don't stop here. This is not your answer. This is 1 over DI. If you have a very small number like this for your DI, you know that you skipped a step and you're not done yet. Okay, so I need to multiply both sides by DI. So then I'll have DI 0.01 is 1. Now I can divide both sides by 0.01. And this will give me a number that is not so tiny, and that's going to be our actual DI. Okay, now, if we had all of our signs correct here, and we put them in here correct, this will automatically have the correct sign. So if there's no negative here, don't add one. Okay, this is our answer, 100 centimeters. Okay, now let's do part 2 of this, right? We found our DI, now we need to find our HI. To find our HI, we have to use this formula. Okay, so I'm going to plug in my numbers. And we have to do this part second because otherwise, we wouldn't know DI because we just had to find that. Okay, so this part is always, this formula is always second. Okay, our DI was 100, but there's a negative here, so we'll have negative 100, and then our DO is 25. And then I'm just going to cross multiply. So I'll have 25 HI equals negative 200. And divide both sides by 25. and I'm going to get -8. Okay, this means that our object or our image is inverted. Okay, that's what that negative means. It just means that the image is inverted or upside down. Okay, so that's how you would solve a problem. And again, we've got all our signs correctly here. So whatever you've got there, just leave it. If you get a negative, good. You've got a negative, you leave it. If you get a positive, good. You've got a positive, leave it. Okay, this was a concave mirror problem. Okay, so now let's talk about convex mirrors. Okay, um, convex mirrors are the opposite of a concave, right? Now, you see your focal point here and your center of curvature here, but the mirrored surface is actually here. Okay, so this would be like if you had like a ball, like one of those, I've seen like a reflecting ball in a garden or something, or like the back of your spoon. A spoon is a really great way to test a convex and concave mirror because the part of the spoon where you put your food in, that you can hold up and it looks like a concave mirror. And then if you flip it backwards, that's a convex mirror. Okay. So now let's try and draw a convex, mirror diagram. Okay. So last time, our first one was pink, so I'll keep doing pink. Okay, so we're going to go parallel again. Okay, and then we're going to go through this focal point. Okay, I'm going to draw it like this, and then I'll continue back this way in case we need it. Okay, so that was our first one, and it really should be connected. And then what was our second color? Our second color was purple, I think. So let's do purple. Okay, so this one is going to go through the focal point. So this one's going to be hard for me to draw straight because it's so far. Okay, so it's going to go through the focal point, and then where that line hits the mirror, we are going to draw a horizontal line. Okay, and then our last one, I think this was green last time. It's going to go from the top all the way to center of curvature. Again, that one's going to be a really hard one for me to draw. Ooh, I try my best in order to get that to work out. Okay, so where these meet, that is going to be where our image is. Okay, so if I had done it correctly, it would meet right here. Okay, it looks kind of confusing because see, like these two, they kind of meet there, but it's actually right here because that's where all the meet. Okay, so it's going to be upright and it's going to be tiny. Okay, so that's a convex mirror, and convex mirrors, they all kind of work the same regardless of how far they are. So we'll see this in the next slide. See, anywhere it is, it's going to be smaller, upright, and virtual. Okay, no matter if it's close or far, it doesn't matter. Okay, now let's do some math for the convex mirror. Okay, so here's our focal length. It's 25 centimeters. See, these are all the same numbers, and the reason I'm giving you similar numbers is because I want you to kind of see how the answer changes based on what type of mirror lens you're using. So the object has a height of 2 centimeters, and it's placed 15 centimeters from the mirror, and we want to calculate DI and HI. Okay, so I'm going to put my focal length, I'm going to put 25, I'm going to leave a space for the sign, because I'm going to come back and add that. My object height is 2 centimeters. Again, I'm leaving a space for the height, or for the sign on that. and then we're going to find DI and HI. Okay, so for a convex mirror, we're going to have our focal length is negative. Okay, our object, it doesn't say our object is upside down, so it's going to have a positive object height, and it's 15 centimeters from the mirror, so we're going to have a positive object distance. Okay, excuse me. Now that I've got these done, I can go ahead and I can solve for my DI. And then once I have my DI, I can find my HI. So I'm going to have 1 over F is 1 over DI plus 1 over DO. 1 over negative 25 equals 1 over DI plus 1 over 15. Okay, so get negative 0.04 for my focal length. Remember, I'm going to just go ahead and turn it into a decimal because it makes the math easier. Okay, now I'm going to put my two numbers together, or my two decimals. Do you see how this time we've got this negative to deal with and last time we didn't? Okay, that's what I mean by the signs. If you correct signs in, it will work out for you. So you don't have to worry about like at the end, like, oh, I need to add a sign. Okay, I'm going to divide both sides. And then I'm going to just do this. I guess I wrote too big on this one. And we get negative 9.09 centimeters. Okay, so that's my DI. Now that I have DI, I can go and I can find my HI. So I'm going to use that magnification formula, HI over HO equals negative DI over DO. Okay, this is the same thing. If your signs are put in here correctly, then you'll get the correct answer. You won't have to worry about adding signs at the end or anything like that. Okay. So you see these two, they'll cross out, right? They'll become a positive. So I've got 15 HI equals 2 times 9.09, which is 18.18, and it's going to be a positive 18.18 because negative and negative is positive. And so now we've got HI equals 1.21 centimeters. Okay, and that means our height is going to be upright. Okay, and this makes sense because remember we saw earlier that in this type of mirror, it's always upright but smaller. Okay, and here we have it's upright because it's positive, and 1.21 is less than 2, so it's smaller. Okay, so that's how we do a convex mirror problem. Now let's talk about lenses. Okay, now this says behind mirror. Should really say behind lens or whatever, but it doesn't matter because it's not a thing. And so these are a little different. If you notice, a convex lens is basically the opposite of a convex mirror. So a convex lens and a concave mirror work the same, and a concave lens and a convex mirror work the same. Okay, so they're like opposites. But here's our plus and our minus, our signs for when we get to do the math. Okay, so now here we go. Here's a convex lens, and sometimes they call this a converging lens. That's why I chose this picture, because it has converging lens on here. So you might see a converging lens or you might see a convex lens. It just depends on how they like to write it. Now, these lenses have basically we draw our lines to like the center of the lens, because remember the mirrors were just like flat. Well, not flat, but they, they weren't thick like this. So this is just kind of, I like to draw a line to show where my center is. Okay, so for a convex lens, I'm going to draw a horizontal, and then I'm going to go through the focal point on the other side. Okay, now I should really go through it. I did the best I can. Now, the next one is going to go angled through this focal point. Okay. Now, do you see how it goes past your lens? That's okay. I'll just draw my line a little longer. And I'm still going to go horizontal. Okay. You see how I'm going to have to lengthen my pink line? That's okay. I can come back and lengthen it. It's not going to kill me. Okay, so it's basically like right on the edge. Okay. So now this image, it's going to be where these two meet, which is basically like right here. So we'll only see like half of the arrow. This is our image. So it's upside down and it's really big. Okay. And this is for between F and 2F. Now, for convex, it's like a concave mirror. There are lots of different choices. And you can also draw one through the center. I always forget that one. I never seem to do that one. Let's see if I can get it to look right. Should kind of go where these two meet. It's close. See, this is why you really need to use an arrow or a ruler, because these little tiny little, bumps, they look straight, but it makes it off just by just the teeniest amount. Okay, so this is how we do a convex lens. And then again, at F, there's nothing. Okay, because we have to draw our lines through F. And so if it's on top of F, and it has to touch the object and F, that's impossible. Okay, so we won't have, we can't do it, so you're not going to get an image. So now we're going to use the same formulas that we had before. It just matters the signs. Okay, so let's see where we're at. We have a convex lens with a focal length of 25 centimeters. The object has a height of 10 centimeters, and it's placed 20 centimeters from the lens. And we want DI and HI. So I'm going to go ahead and draw my, or write my, what I know. And again, I'm leaving that space for the plus or minus so I can add that part. Okay, so for a convex lens, our focal point is positive, or our focal length, so I'm going to put positive here. It doesn't say our object is upside down, so our height is positive, and it's in front of the lens, so our object distance is going to be positive. Okay, and then we can go ahead and we can do some math. So to get our DI, again, we use the same formula. Okay, I'm going to put my numbers in here. sorry, should be a minus. Okay, so I'm going to get negative 0.01. This is not my answer, remember, right? It's too tiny to be my answer. I need a number that's bigger. So that reminds me that I need to go ahead and do some algebra. Now, you don't actually have to do this algebra. You could just do, you could just know that you need to do 1 divided by whatever that number was, and that would be fine. But I'm doing it just for your benefit. And so I'm going to get negative 100 centimeters. Okay, this negative is here. That's what I got. So that means I have a negative image distance. I'm not going to change it. Okay, do not change it. Now, I'm going to find my image height. So I'm going to use this magnification equation. So I'm going to do HI over HO. So I'm going to have 20 times HI, because I'm going to cross multiply, right? And then I'm going to have 10 times 100, and it's going to be a positive 100 because we have negative and negative. And then I'm going to divide by 20. And my HI is going to be 50 centimeters. Okay, since it's positive, that means it's upright. Okay, and it's going to be larger because you see how this one was 10 and this is 50, so it's going to be larger, our image. Okay, so that's how you would do a convex lens problem. Okay, so now let's go to a concave lens. And we're going to draw the same type of images. I highly recommend that you practice these, or at least you memorize that chart. Since it's virtual school, it'd be very difficult for us to make you draw these on a test, right? Um, okay. So there's the center. I'm going to do a horizontal here, except instead of going horizontal and through this focal point like I did with the convex lens, I'm going to go through this focal point. Very good. Yeah, let's show that now. Okay. So there's oops, I did this wrong, sorry. Sorry about that. It's from, since we already did from here to here. Remember how this one we did from here to there? So we should do from here to the focal point, which is more difficult to draw, of course. Oh, actually, I did pretty well with that. I'm impressed with myself. So that's that one. Then do another one. So for this one, we're going to go angled through this focal point. So try my best to get it to be straight. Here we go. And then this should be straight like that, but it doesn't look super horizontal. Okay. And then our image is going to be maybe to mute. Okay. So that's how you would do a convex lens. Okay. Now, for these, or concave, sorry, they're going to be smaller, upright, and virtual every time. And then we're still going to use these same formulas, except it'll just matter what we do our signs. Okay, so let's get started. So a concave lens has a focal length of 25 centimeters, an object height of 10, and we're putting it 20 centimeters from the mirror. And we want our DI and our HI. Okay, so I'm going to write what I know, and I'm going to leave a space for those signs. I'm going to add those after. So my focal length is 25, my HO is 10, my DO is 20, and I've got a DI and HI. Okay, now for a concave lens, the focal length is negative. Okay, it doesn't say that the object is upside down, so the object distance or the object height is positive. And it doesn't say the object is on the other side of the lens. It's on the side it always is, the left. And so our object distance is also going to be positive. So now that we have that, we can do some math again. I would definitely expect to have to do this math on the test. So I would, try at least a few problems so you're comfortable with it. Right? It looks like it's easy to me because, I've done it a million times. But, that was my first time doing it on the test. Like, for example, before I see you guys at night, I actually work through the problems myself just to make sure I remember how to do them and I don't make any mistakes and that kind of thing. And then when I get to you guys are like, wow, she knows exactly how to do that. That's because I've already done it at least once today, right? So, if I'm doing it at least twice, it would make sense that, you guys might have to do these problems more than once, or at least problems like this more than once in order to, feel comfortable with them. Okay. So I'm going to have DI and divide by and I'm going to get a DI is equal to negative 9.09 centimeters. Okay, now that I have that, I can go ahead and I can try and get my image height. So you see I've got a negative and a negative. So that's going to make it positive. Now I'm going to cross multiply about 20 times HI, and then 10 times negative 9.09, which is 90.9. Well, it's actually negative and a negative, so it's positive. And then divide by 20, divide by 20, and my HI is going to be 4.55 centimeters. Okay, since that's positive, that means it's upright. And the initial object height was 10, and this is 4.55, so it's going to be smaller. Okay, so that's how you solve that. Now, I've done a problem of each type, each of the four types, right? Concave lens, convex lens, concave mirror, convex mirror. And then I've also done a ray diagram of each type. So hopefully, um, if you get confused with those, you can go back, and go to that spot and you can kind of practice those. Um, I'm going to go back to these deadlines again, just so that's the last thing that you guys see. And then hopefully those diagrams and those problems were helpful to you.